Hello students, welcome to EPG Pathshala. I am Dr. Anjali Sharma from University of Delhi. Today we are going to discuss about the module Hamiltonian and the stress tensor from paper Electromagnetic Theory. So students, let us see what we are going to learn in this module. Hamiltonian formalization for fields and the canonical stress tensor, the covariant generalization of Poynting Theorem and the law of conservation of energy, problems with the canonical stress tensor and their elevation by symmetric stress tensor, the covariant form for the angular momentum of the field. In the introduction, here we'll see when we give a Hamiltonian description of field theory, in particular the electromagnetic field. As we know very well in particle mechanics, the transition from the Lagrangian to Hamiltonian formulation is made by first defining the canonical momentum variables by Pi, which is equals to del L, which is dependent on Qi, Q dot I and T divided by del of Q dot I, where I takes the value from 1 to up to n. L is the Lagrangian, which is to be regarded as a function of the generalized coordinates qi and generalized velocities qi dot, which may be ordinary coordinates and velocity, and perhaps an explicit function of time t. The Hamiltonian is then defined through h dependent on qi, pi and t is equals to summation over I of pi into qi dot minus L dependent on qi, q and t. Now note that the Hamiltonian is to be regarded as a function of qi, pi and t. It then follows from Hamiltonian's equation of motion that if the Lagrangian is not explicit function of time, that is, if dl by dt is equals to 0, then dh by dt is also equals to 0, which means that the Hamiltonian is a constant of motion. This is an expression of conservation of energy. The Lagrangian approach to field theory was introduced in the last module. As we explained there, the approach to continuous fields closely parallels the techniques used for the discrete point particles in mechanics. The finite number of generalized coordinates of qi t and generalized velocities qi dot t, where I takes the values of integers from 1 to n, are replaced by an infinite number of degrees of freedom. Each point in space-time x raised to power alpha corresponds to a finite number of values of the discrete index I. The value of field at each point in space is a coordinate. So students, let us see the canonical stress tensor. Similarly, we need to construct a Hamiltonian density H whose volume integral over three-dimensional space H can be interpreted as energy. The Lorentz transformation property of H can be guessed as follows. Since the energy of a particle is the time component of a 4 vector, the Hamiltonian should transform in the same way. Since H is equals to integral of H d cube x and the invariant 4 volume element is d4x equals to d cube x dx naught equals to c d cube x dt, it is necessary that the Hamiltonian density transformation as the time component of a second rank 4 tensor. From the Lagrangian density L phi kx del raised to power alpha phi kx, we construct the Hamiltonian density in analogy with the earlier equation as H equals to summation of k del L divided by del of del phi k by del t into del phi k by del t minus L. The first factor in the sum del L by del of del phi k by del t is the field momentum canonically conjugate to phi kx, and del phi k by dt is equivalent to the velocity q1 dot. The infrared Lorentz transformation property of H suggests that the covariant generalization of the Hamiltonian density is the canonical stress tensor having T raised to power alpha beta is equals to summation of k del L by del of del alpha phi k into del beta phi k minus g alpha beta L. For the electromagnetic field, the field variables are a raised to power alpha and del beta a alpha. So we make the replacement phi k tends to a raised to power alpha into del beta phi k, which tends to del beta a alpha. So that T alpha beta is equals to del of LEM by del alpha a raised to power lambda into del beta a raised to power lambda minus g alpha beta LEM. For the free electromagnetic field, the Lagrangian is L free equals to minus 1 divided by 4 mu naught F mu v into F mu v. So that del of L free divided by del of del alpha a lambda equals to minus 1 divided by 4 mu naught del of F mu v into F mu v divided by del of del alpha a raised to power alpha equals to minus 1 divided by 4 mu naught into del of F mu v divided by del of del alpha a raised to power lambda whole into F mu v plus del of F mu v by del of del alpha a raised to power alpha into F of mu v. Let us look at the first term. Using the relation between the field and the potential, F mu v is equals to del mu Av minus del v A mu. So then we can write del by F mu v by del of del alpha a lambda into F mu v is equals to del of del mu a v minus del v a mu divided by del of del alpha a lambda whole into F mu v, which is equals to g mu alpha into F mu lambda minus g v alpha into F lambda v equals to 2 g mu alpha into F mu lambda. The second term also produces the same result, so that del L free by del of del alpha a lambda equals to minus 1 divided by 4 mu naught into 4 g mu alpha F mu lambda equals to minus 1 divided by mu naught g mu alpha F mu lambda, and T alpha beta is equals to minus of 1 divided by mu naught g alpha mu F mu lambda del beta a lambda minus g alpha beta L free. In terms of electric and magnetic field, L free is equals to minus 1 divided by 4 mu naught F mu v into F mu v equals to 1 divided by 2 mu naught into E square by C square minus B square. So T 0 0 equals to minus 1 divided by mu naught G 0 mu F mu lambda del 0 A alpha minus 1 divided by 2 mu naught into E square minus B square into G 0 0 minus 1 divided by mu naught C square E dot del A by del T minus 1 divided by 2 mu naught E square by C square minus B square. Now from the definition of electric field in terms of potential, minus of del A by del T is equals to E plus del phi. Further, del dot E is equals to 0, so that T 0 equals to 1 divided by mu naught C square E dot E plus del phi minus 1 divided by 2 mu naught into E square by C square minus B square equals to 1 by 2 into epsilon naught E square plus B square by mu naught plus epsilon naught del dot phi E. The first term is the expected energy density. The second term is additional. And if we suppose that the fields are localized in some finite region of space, then the volume integral of the last term vanishes and thus will get integral T 0 d cube x equals to 1 divided by 8 pi integral of E square plus B square into d cube x equals to W field. The usual expression for the energy of the electromagnetic field. Now let us look at the T0I component of the stress tensor. T0I equals to minus 1 divided by mu naught G0 mu F mu lambda del I A lambda equals to minus 1 divided by mu naught F naught lambda del I A lambda, which is further equals to 1 divided by mu naught C into E1 del A1 by del xi plus E2 del A2 by del xi plus E3 del A3 by del xi equals to 1 divided by mu naught C Ej del Aj by del xi. Further, E cross Bi equals to E cross del cross A whole I equals to epsilon ijk into Ej into epsilon klm into del by del xl am is equals to Ej del Aj by del xi minus Ej del Ai by del xj. Hence, Ej del Aj by del xi equals to E cross Bi plus Ej del Ai by del xj equals to E cross B whole I plus E dot del Ai equals to E cross Bi plus del dot Eai. So that TOI equals to 1 divided by mu naught C into E cross B whole I plus 1 divided by mu naught C del dot E into AI. Once again, apart from the expected momentum density term, there is an additional term which vanishes on integration over all space. Integral TOI d cube x equals to 1 divided by mu naught C into integral E cross B d cube x equals to CPI field. Similarly, T I 0 is equals to 1 divided by mu naught C E cross B whole I plus 1 divided by mu naught C into del cross phi B whole I minus del by del x naught of phi E I. Evidently, the canonical stress tensor T alpha beta is not symmetric. This is clear from the definition itself, since it contains the term del beta A lambda but not its counterpart del lambda A beta. Poynting Theorem. The connection of the time and time-space components of T alpha beta with the energy and momentum density of the field suggests that there is a covariant generalization of the Poynting theorem or the differential conservation law of energy. That is, del alpha T alpha beta is equals to 0. We prove this relation from general case described by the tensor and Euler-Lagrange equation. Now consider del alpha T alpha beta equals to summation k del alpha into del L by del of del alpha phi k del beta phi k minus del beta L, which is equals to summation of del alpha into del L by del of del alpha phi k into del beta phi k plus del L by del of del alpha phi k into del of alpha del beta phi k whole minus del beta L. On using Euler-Lagrange equation, del alpha del L by del of del alpha phi k is equals to del L by del phi k. The first term above can be transformed and we obtain del alpha T alpha beta equals to summation k del L by del phi k into del beta phi k plus del L by del of del alpha phi k into del alpha del beta phi k whole minus del beta L. By the chain rule of partial differentiation, the first term also equals to del beta L and hence del alpha T alpha beta equals to 0. On integrating over all space, 0 equals to integral of del alpha T alpha beta d cube x equals to del naught integral T0 beta d cube x plus integral del I T I beta d cube x. The second integral, being a divergence, vanishes on use of Gauss theorem and hence we get del 0 integral T0 beta del cube x equals to 0, which implies that dw field by dt is equals to 0 or dp field by dt is equals to 0. And here we recover the laws of conservation of energy and momentum. The symmetric stress tensor. The canonical stress tensor T alpha beta, while adequate so far, has a certain number of deficiencies. Evidently, the canonical stress tensor T alpha beta is not symmetric. It is clear from the definition itself, since it contains the term del beta A lambda but not its counterpart del lambda A beta. Though the integrals of T00 and T0i represents the energy and c times momentum respectively, T00 and T0i differ from the expression for the energy and the momentum densities. Further, the canonical stress tensor involves the potential and the expression therefore is not gauge invariant. Finally, we add that the trace of T alpha beta is not 0 and a requirement that comes from the zero mass of the photons. To obtain a symmetric traceless Gauss invariant tensor, phi alpha beta from the canonical stress tensor T alpha beta, we proceed as follows. From the definition of the field tensor, we have F beta lambda equals to del beta A lambda minus del lambda A beta, which implies that del beta A lambda equals to del lambda A beta minus F beta lambda. On substituting this into expression for T alpha beta, we get T alpha beta equals to 1 divided by mu naught into G alpha mu F mu lambda into F lambda beta plus 1 by 4 G alpha beta F mu V F mu V whole minus of 1 by mu naught G alpha mu F mu lambda del lambda A beta. The first two terms are gauge invariant and symmetric. On using the homogeneous Maxwell's equations, del lambda F lambda alpha is equals to 0, and the last term can be recast as T alpha beta d is equals to minus 1 divided by mu naught G alpha mu F mu lambda A beta equals to minus 1 by mu naught F alpha lambda del lambda A beta, which is further equals to 1 divided by mu naught F lambda alpha del lambda A beta plus A beta del lambda F lambda alpha, which is further equals to 1 divided by mu naught del lambda of F lambda alpha A beta. Now del alpha T alpha beta d is equals to 1 divided by mu naught del alpha del lambda of F lambda alpha A beta whole equals to 0. Since del alpha del lambda is symmetric while F lambda alpha is antisymmetric, hence volume integral T 0 beta d cube x equals to volume integral 1 divided by mu naught del dot A beta E d cube x equals to surface integral 1 divided by mu naught n cap dot A beta E dA equals to 0. We now define the symmetric tensor phi alpha beta equals to T alpha beta minus T alpha beta d equals to 1 divided by mu naught into G alpha mu F mu lambda F lambda beta plus 1 divided by 4 G alpha beta into F mu V into F mu V with the following properties. Phi alpha beta equals to phi beta alpha, T phi is equals to 0, and del alpha phi alpha beta equals to 0. Phi 0 0 equals to 1 by 2 mu naught E square plus B square by mu naught. Integral of phi 0 0 d cube x equals to W field. Phi 0 I equals to phi I 0 equals to 1 by C mu naught E cross B whole I, and integral phi 0 I d cube x equals to C pi field. Phi ij equals to minus epsilon naught ei ej plus 1 divided by mu naught bi bj minus half of delta ij into epsilon naught e square plus b square by mu naught. Recall that phi 0 0 is the energy density of the electromagnetic field. Phi 0 I is c times the momentum density of electromagnetic field. Phi ij is the negative of Maxwell's stress tensor Mij. The tensor symmetric stress can be written in a schematic block matrix form as phi alpha beta equals to mu Cg minus Tij m. The differential conservation law delta alpha phi alpha beta equals to 0 embodies Poynting theorem and conservation of momentum for free fields. 0 equals to del alpha phi alpha 0 equals to 1 by c of del mu by del t plus del dot s. This is the Poynting theorem in the absence of sources. 0 equals to del alpha phi alpha I equals to del gi by del t minus summation j equals to 1 to 3 of del by del xj of Tijm. This is the law of conservation of momentum in the absence of sources. In particle mechanics, the angular momentum of a system of particles can be defined through the antisymmetric tensor, that is Mij equals to summation for all particles of xi pj minus xj pi. This tensor has three independent components which together form the angular momentum, that is equals to r cross p. Extending this idea to four-dimensional space, we define an antisymmetric tensor m alpha beta by m alpha beta equals to summation for all particles of x alpha p beta minus x beta p alpha. The three space components Mij represent angular momentum of the system. Mij equals to constant expresses the conservation of angular momentum. We conjecture that the full conservation law is m alpha beta is equals to constant. Then mi0 is equals to constant, which implies that summation of xi w by c minus c t pi is equals to constant. This implies that summation xiw by summation w is equals to summation c square t pi by summation w plus constant. The sum on the left hand side is the position of the center of mass of the system, that is RCM is equals to summation gamma mx divided by summation gamma m, while that on the right is t times the center of mass velocity. Thus, we obtain VCM is equals to summation gamma mv by summation gamma m, which is a reasonable result. Angular momentum for the field. We define the angular momentum density m alpha beta gamma equals to phi alpha beta x gamma minus phi alpha gamma x beta. The covariant generalization of usual angular momentum density, then del alpha m alpha beta gamma equals to 0. This is the differential form of law of conservation of angular momentum for the field in the absence of sources. The symmetry of the stress tensor is quite crucial to this proof of conservation of angular momentum. We had also used the canonical stress tensor instead. Conservation of angular momentum would have not been possible. So students, let us summarize what we have learnt in this module. Hamiltonian formulation for field has been described. Canonical stress has been introduced. The Hamiltonian density is a component of a second order stress has been represented by the canonical stress tensor. The formulation is then developed for the electromagnetic field in particular. The covariant generalization of the Poynting theorem, the law of conservation of energy, has been given. The covariant generalization includes the law of conservation of energy and of momentum. Problems with the canonical stress tensors have been discussed and the symmetric stress tensor introduced, which eliminate these problems. The covariant form for the angular momentum of the field is given that needs the introduction of a third rank tensor. The law of conservation of angular momentum is then obtained in terms of this third rank tensor. Thank you.